The offshore won't listen to anyone else. They barely listen to me.
Alrighty, friends, we're going to go ahead and get started. We're going to get started. My name is Michael. I am a systems engineer for the Department of Defense, and I'm also a master's student at Georgia Tech. And so that's where I get a lot of my inspiration from, is I'm going through a bunch of different machine learning and artificial intelligence related courses. And then I also have a background. I was a nurse before I was an engineer. Did a whole bunch of stuff trying to go to medical school, so I still have a very big interest in neuroscience and psychology. And I'm constantly thinking about how we can try and bridge the two, or if we should even bridge the two, or we need to find like a whole new approach. So a couple of things that I like to say up front. I took the liberty of using AI to create these slides. I don't like PowerPoint presentations. I'd rather it be a conversation, so these are just more here to guide us rather than they are to actually be the presentation. I didn't make this title, AI did. So with that, you don't even have to say next slide, look at that. I wanna make sure we get, like, we're all operating from the same baseline understanding of what intelligence is, and then also what is artificial general intelligence. So I wanna open it up to you guys, and let's first start with, like, can someone just throw out what they think intelligence is from just like a general perspective?
Learning new things.
Okay. So can we take it a little bit further? So like if we're learning new, like is learning something enough?
Being able to do something with that knowledge.
Right. Okay, so if we, go with that?
Ability to decide.
Ability to decide.
Ability to create something
Okay.
out of,
Can you say that one more time?
create something out of nothing.
Sure. And so, go ahead, Lawrence.
Ability to recognize and solve problems using previous information.
Perfect. So what I was looking for there is we're able to take new information and solve a problem with it, right? That's a bit narrow, but it's something we can work with. And so when we're looking at, if we want to extend this to like machine intelligence or machine artificial general intelligence, which is a word we hear thrown around pretty often, the way I think about it is you have a model, a deep learning model that can take in data about its environment or its world state, and it can use that to solve problems and novel problems. When you take something that I want to kind of put on top of that is when you look at like the traditional media narrative or what we think about, there is also an implicit and explicit statement of AGI will do it significantly better than we can, right? I think that is inherent in the narrative and why we're pursuing it, so that we get something that can be a better problem solver than a human. If we want to think about that mathematically, which I think is helpful, essentially what deep learning does is it takes input data and it maps a function to the data such that it can solve problems. We're going to call that function G. If we've achieved AGI, then a deep learning model should be able to continuously update its G function such that it's better than its prior G function. So if we go from G to G+1 is better at solving problems in the world that it's operating in than G. And then it'll do G+2, and then G+3, and then it'll get so fast that we end up in this recursive loop that it's theoretically able to solve all the world's problems.
How does the function there differ from artificial intelligence, artificial general intelligence? Since it's delimited by the world, isn't that just general versus everything else?
So I think that I'm not sure I understand your question.
The underlying question is, can you define AGI, the general part specifically, versus anything else so that I understand where you're coming from?
Sure. I mean, I think for me, general, so let's use an example. So if I were to look at something like a convolutional neural network that was trained on medical images to diagnose cancer, it can very specifically do that thing and only that thing.
Yes.
It cannot solve any other problem space. When we're looking at artificial general intelligence, the idea, I believe, is that it's able to solve problems in the entire problem space.
And if we were talking about an LLM, would you consider that does not count as AGI because it is solving problems in a language space?
I very specifically use the word AGI because I think LLMs have dominated the term AI. And so that's why I've chose to use AGI. Does that, that's a very backwards way of answering your question, but does it?
But I'm seeing the delineations now, so I think that's enough. Thank you.
Sure. What's up, Kevin?
So who decided that humans have general intelligence, right? Because when I'm thinking about it, it's like I personally can't look at a medical image and diagnose somebody, right?
So I'm going to talk about that later, right? As a civilization, we have intelligence.
Okay, right. Okay, so as a civilization, we have, general intelligence. As in, there are some people who are able to diagnose, right? But you can also make the argument that there are some models that can diagnose cancer by looking at pictures, and there are some models that can look at text and do stuff with text, like
Correct.
LLMs.
Yeah.
So you can also just say that the set of all possible models that you're generating with neural networks, doesn't that also say, okay, we have general intelligence?
Go ahead.
And I think this is why the slide comes up here. Why is it intelligence? What is the definition?
Yes.
That in of itself is a very complex problem. What is the question? Is the question. And to your point, is cooperation an essential component of intelligence? And general intelligence means that things can cooperate, that it can adapt to its environment, but also with the cooperation of others, change that environment. And where do you draw the line? So, I mean,
That's like a
are humans intelligent? We're asking as human, but what other things are intelligent?
And we're going to...
There are things that are intelligent that are not necessarily cooperative.
So
Okay,
I
give me
won't-
an example. Right, sorry.
No, go. You can give your example, but there's a back half of this presentation that talks about humans, and so I would like to push your conversation to the back half, where we're engaging specifically about how humans, the specific methods that not just humans, but biological organisms in general have gotten to where they are today in their form of intelligence.
Okay.
Yeah. Did you want to go ahead, sir?
One thing I would add is I think maybe just talk about it a little bit is I think it's important to realize that intelligence not necessarily means that what you can do now, but rather that we have the capacity to learn and patterns that over time we become experts at something as we continue to train our latent memory on a certain domain of knowledge, but we also have the capacity to interpret and observe patterns to that environment. I think, to me, that's what intelligence is.
Yeah.
Like a baby can be very intelligent, but they can't diagnose any medical conditions.
Right.
They might in 20 years.
Yeah. And so that's you're touching on kind of this problem of for something to be intelligent, I think fundamental, and we can disagree on this all day, we're just trying to get something we can all work off of, right? Fundamental to the idea of intelligence is you're able to take in data and update your priors such that you can interact in the world in a new way. And that's kind of where I want us to think about that, right? So we're going to hone in on that G function just to keep it simple. My G function is how I solve problems today. Tomorrow, I'll have a G+1 function where I solve problems better today, or better tomorrow than I did the prior day. Do we all agree on that? Can we all move forward on that? And even if we can't, we're going to the next, oh, he already did it. All right. Okay. So now we're going to start diving into the specifics about how deep learning actually learns. But what I really want to try and achieve is I know that all of us are going to be at different levels of where we're at in our computer science journey, whether we're brand new, or some of you guys are probably very senior at this and you're going to be like, Michael, you're wrong, you're stupid. Just tell me after the presentation and I'll make a note in Discord of all the things that were wrong. And so I really like this carbonara example. So let's just say that there's a head chef. He comes and he tells us, I want you to make carbonara. And all he tells us is the ingredients. You need noodles, water, eggs, Parmesan cheese, and bacon. Or if you're wealthy, pancetta. That's all they tell us, right? I go and I throw the ingredients together into something that looks like pasta. And I come back to I forgot salt. Salt's really important. I come back and I tell them, I give it to the chef and he tries it. And all he says is, you overcooked your bacon. So I go back to the drawing board. But this time I have a little bit information to update my process. I cook my bacon faster, or I don't cook it as much. I come back. He's like, hey man, you don't have enough salt. It tastes bland. I'm like, all right, cool. I go back, I try adding a little bit more salt. I come back, he says, you still don't have enough salt and your noodles are raw. So I go back and I cook my noodles longer and I add more salt. And we just get stuck in this continuous loop of I make a guess about how to do it, I get a feedback, I update how I do it, I make a guess, and we're in that loop. Does that seem pretty easy to understand? Okay. All right. So what we're going to do now is we're going to start diving into the technical mechanisms of how deep learning goes through this process. And the first part of that is going to be your forward pass. Next slide. This is an AI-generated slide. I don't like it. Y equals mx plus b is the formula we're going to use for our forward pass. M are your weights. And so when I get told, so I have a weight for salt. And maybe at whatever point, it's 0.1 tablespoons. And then I get told that I have too much salt. I'm going to update the weight for salt so that I put less salt in. X is the input itself. And B is the bias. All right, let's go forward one. And so what we're going to do is build a computation graph. And this is mainly to help visualize how we go through this process. PyTorch, things like PyTorch kind of do this automatically in the background. But it is helpful to walk through and see how it's done. So the first step is taking your input data and timesing it by your weight. And that gives us an intermediate value z, or 3 times 5, which is 15. And then we add our bias to it. This gives us 15.03. Go ahead, go forward. Okay, so this is probably the first, I think, kind of hard part about the forward pass. And that is this softmax function. So if you look at so I think the example that AI chose to use is we're predicting an image, and we have 3 options. We have cat, dog, and bird. We got these values. These are our predictions. 15.3 is higher than all the others, so it's telling us that cat is a prediction it wants to make for the specific image that it's seeing. However, these are very difficult to compare to each other outside of the fact that one is larger than the other. So what we want to do is normalize them so that you now have a better comparison about how heavily each one is weighted towards the correct answer. And you do that via the softmax function. The softmax function first takes everything, first exponentiates it. So you end up with e raised to 15.3, which gives you 4,413,000. You do that for all of the potential answers, which gives you a sum. And now you take 4.413 divided by the sum, which gives you our probability currently that this is a cat is 72%. Our probability that it's a dog is 22%. Our probability that it's a bird is 6%. Go ahead, Saul.
And what do you mean by normalize? So it's normalizing the result.
I'm going to have you explain that.
Put it between 0 and 1.
Oh, sure. Yeah, sorry. So that's a really important part, too. It squashes everything between 0 and 1. So you're always going to get a result that's between 0 and 1. And there are other functions that will not bound you between 0 and 1, and you have to pick which one's best for your use case. Go ahead.
Instead of, from a comprehension perspective, I think instead of saying 0 and 1, it might be worthwhile saying that it's saying from definitely not 0, 100% certainty, and the sum of all the components
and a really,
It's only of the results. It's not of all existence.
No. I'm just saying
It's
that
of these.
from a computation perspective, that normalization is notionally connecting that to certainty.
yes.
From definite certainty of not being in the set to definite certainty of being within the set. I think that's what she's doing. I find too many tutorials that don't talk about that connection.
Yeah, no, and that's really important. And it talks about this really, it's also a really interesting characteristic of the softmax function. It'll never be 1. Or you'll never have a probability that's a part of the softmax function that is 1. A deep learning model will never be so confident that it knows with 100% that this is the correct answer. And so it's always continuously trying to improve, and like theoretically you could only ever hit 0.9999999.
And it's not, you said the word correct answer. It's the correct answer of the givens. It might not, the picture might not be a dog or a cat or a...
Correct. Well, we're assuming based on the data.
We're within the data, that's my point.
Yeah, within the data.
Within the data.
Yeah.
Based on what it's trained to do and its intelligence, this is its prediction and its confidence.
Yes. That's what I'm just saying. It's like if something says it's 99% sure that this is correct, that doesn't mean worldly true. That's not 99% true.
It could
Sure.
be wrong, separating 99%.
But it won't hit one.
It won't ever hit 1. For cat specifically, it'll never hit 1. The function itself will always add to 1. The inputs to the function will always add to 1, but cat will never be 1. Yeah.
Okay.
Yeah.
Ignoring any like integer floating point rounding.
Yeah, I don't need that kind of nuance, sir. All right. Okay.
We're all thinking it.
So for all intents and purposes, like, we can go back this way and we can start the revision process, but this is its prediction. However, if you go one slide forward, we have this thing called the cross entropy loss. This is important because it's going to indicate to us how much we need to update our weights so that we can get closer to a correct value. This is that loss, you don't have to go back. That loss, if we were doing a multi-layer network, that loss is also what will get propagated to the next layer of the network.
Lost backward in PyTorch parlance.
That's right. Okay, so go forward. So before I move forward, do any of you guys have any questions? And do any smart ML engineers have any rebuttals?
My rebuttal is that this is overkill to fit a linear function.
It's overkill to fit a linear function?
To fit a linear function.
Okay.
That's
Alright.
it. I mean, you can also compute the...
This is for learning.
Oh.
I could throw a convolutional neural network formula up there if you want, but we'll be here all day.
You asked me for a rebuttal, and my rebuttal instead of cross entropy loss.
I never said I'd agree with the rebuttal. What's up, Lawrence?
So you had discrete categories of dog, cat, and bird. Is that an oversimplification of how this works in production, or is that a known limitation? For example, what if you have cat, dog, right? That's not clearly in the categories of cat or dog.
Yeah, so I think it's always going to depend on your use case. And so that's where you start getting into things as well, like binary cross entropy and versus like a multi-class cross entropy, where you might. So for example, if I'm a patient, I might have a radiological image that I am positive for both cancer and pneumonia. In that particular case, you're going to need a model that is more apt to not do just pure discretes 0 or 1. It might be able to do discretes across all, but it can also do continuous values as well. It just depends on how you train the model. So I wouldn't say that's definitely not a limitation of deep learning today.
Okay.
Yeah. What's up?
Okay, so is entropy synonymous with information in this context, or do you want to just explain the cross entropy meaning in this context
Can you help me with that, Saul?
of the jargon?
When you were talking about entropy and information, we come back to Boltzmann's derivation of thermodynamics. That's what
So this isn't Shannon's entropy information theory?
Yes, but Shannon gets it from
Oh, I thought these were two different things.
So it's all derived from the same idea, and that's why you see the logarithm, to put it in terms of what is the probability, this idea of entropy.
So,
In this case, it's doing it across the different possible values, and you pointed out that it's a discrete set of possibilities.
Why is it cross in this context?
Because of discrete possibilities.
Okay.
can you give a qualitative description, like if that number was higher, what would that imply? And if it was lower, what would that imply? Just qualitatively speaking.
Yeah, so correct me if I'm wrong, Saul, but the higher your loss, so your goal with each epoch or each loop of training, you want your loss to go down. Your loss is telling you you are more probabilistically correct than not. And so the higher the loss, as we're going backwards, that's going to affect the way we update our weights more impactfully than it would if the loss was lower. Is that fair?
Yeah.
Okay.
Yeah.
Okay.
So you're thinking about that difference between what your model predicted and what the outcome was as a loss function.
And you're trying to find, and you're still trying to keep your patterns generalizable across your whole true data inferencing, not fine-tune those are exact examples. So that's the loss. If you turn it too far, you overtrain.
Yeah. Yep. So, all right. So that is how the model is going to make a prediction. It's going to take its weights, it's going to multiply it by an input, it's going to put it into the softmax function, and it's going to theoretically use its highest probability output out of the softmax function, and that's its prediction. When you're first training a model, it's incredibly likely that its prediction is going to be wrong. And so you need a way to nudge it so that it's more likely to produce the correct probability. And so what we're going to start doing now is the backward pass. So this is that part of the carbonara example where the chef just told me I had too much salt. I need to go update my weights so that I can try and get the correct amount of salt. And so we did the forward pass. Now we're going to do the backward pass. And it's going to require some calculus, specifically the chain rule and derivatives. But that's okay. We're going to try and make it easy, which is another reason why we used an easy example. Go forward for me. I skipped an easy step here. It turns out that the derivative of the softmax and the loss part is just, I believe it's 1 minus your probability. And then you get your derivative. I suck at proofs, so I don't really want to go through that. Just trust me on this one. Take these two, 1 minus the probability that you had. Is that correct, Saul? That's because this is negative. Is it probability minus 1? I think it's probability minus 1.
I think so.
Yeah, it's probability minus 1. I'm quite confident on that. Did you have a question? Did you raise your hand? No? Okay, all right. Okay, wonderful. So now what we got to do is we're going to do two things. We got to find the derivative of the loss with respect to b. And the way we're going to do that is by taking the derivative. Can you go forward one for me? Good, sir. We're going to do that by taking the derivative of y with respect to b and then multiply it by the first part of the derivative that we did. What's up?
Can you explain if we're talking about derivatives, why it's like that symbol? I don't know what that Greek symbol is called, and not the dl over dv.
I think that's just a fancy d in my mind.
Okay.
That's the way I view it. Do you have something?
It's a partial derivative.
Oh, so you knew the answer, and you're just probing me?
I was hoping that you'd be able to explain why partial derivatives here is used, but
I gotcha. I don't know. Saul, do you know the answer to that? Why we would use partial derivative in this case?
You're doing it for each of the variables in turn. So your output of that whole system was a series of values. So you're really getting like a matrix coming out. And you're trying to figure out for each of those values the salt in the recipe, how long you cook the pasta.
Mm-hmm.
Can I get a value out from that for each of those where it is right now and how far it should move the other way? Because you think about if you hadn't gone through this process, then you could add 100 pounds of salt to your recipe, which wouldn't make it better. You know, a teaspoon. Okay. So the measure for that, the rate of change that you apply, that partial differential, is a small value for this. Your length of time for cooking might have changed dramatically, depending on how your results come out.
Mm-hmm. What's up?
Just to make sure that my internal thought here is correct, because again, you were talking rates of change. I've discussed this with other people, so I think it's right, that for the case of cat, bird, dog, that's really nice, that's three, we're used to thinking in 3 dimensions. We are building a local 3-dimensional slope for the point that we are at, and we are then going to move in a direction on that slope down. Up,
Yeah, gradient
whichever
descent.
way.
Yep.
Yes.
Yeah.
But that is why it's a derivative. You can change that from 3 up to however many discrete outputs you have. That is still going to be an n-dimensional space where you are moving in a direction across it by a certain amount, and I don't understand the amount there.
I gotcha. So are you looking for clarification on the amount that we get, or are you just trying to express the way you're thinking?
I'm trying to express it, and I'm getting nods, so it's good enough.
Okay. Yeah. We'll talk about that a little bit further. A couple slides forward, we'll kind of talk about that like gradient descent process. Because ultimately what we're trying to do is, you could imagine we have a valley, and we're really trying to kind of find the global minima in that valley, i.e. the gradient descent. If the gradient signal is correct, it should be leading us down the valley such that our loss is becoming lower. Okay, go back one. We weren't done. Turns out if you're adding, it's really easy. The partial derivative is 1. And then we got the chain rule, so we get times negative 0.28, which means our gradient value, the update value, is going to be negative 0.28 for bias specifically. Now, go forward, please. So we got to do the same thing for your weight. You can go forward again. And it's just the exact same process. So when you take the partial derivative, you take, I always get confused. I should have labeled these better. I believe the input was 3. No, the weight is 3, the input is 5. So this goes away and you use your input, and then you times that by the first part. So that's your derivative times your chain rule portion. And then, so I don't know, I can't do that kind of math in my head, so go forward one. So this is, oh, go back one. I did a very bad job with these slides, guys.
I did a bad job with slides.
What's that? AI did a bad job with these slides.
That's not your fault, yeah.
So this will result in, 2.5 of 5 is like 1.25. So we're at like negative 1.25 is our gradient update value for the weight. Okay. We're gonna go forward. So now we have our update values. We're gonna use something called an optimizer. There's many that you can choose from, but one of the first that you learn about is stochastic gradient descent.
It's terrible, don't use it.
You should use Atom at a default or Atom W. And so it's pretty simple. It's your new weight equals your old rate minus the learning rate times the gradient. We used an assumed value of 0.01 for the learning rate. You get to set that. That is a controllable parameter that you will fine tune to find the right learning rate. So then what you do is you take your learning rate times your gradient, and then you subtract that from your old value. In this case, since we have a double negative, it turns out bias actually needed a higher weight. And then you would do this for your weight, your weights as well. You would use the same update rule. And then we would start at the forward process again, where we take our new 0.3028 and we add that to the weight times the input, which maybe that gives us 0.76 for cat instead of 0.72. And if the true label is indeed a cat, then we went in the right direction. What's up?
So what happens when the learning rate is too high? Like I want a model with a very high learning rate.
Yeah.
Doesn't that mean it gets harder?
Nope. So back to your question. the learning rate determines how quickly you descend down your gradient descent. And so, and I'm going to need your help on this one, Saul, but my understanding is that if the learning rate is too high, it actually ends up bouncing back and forth. You overshoot a good local optima, and then when you're in this good, you overshoot it, you're in a bad place, and then you just send yourself back to the other side of a good local optima. And so when you look at the graph, instead of just seeing this nice descent downward, you end up with this oscillation stuck in a specific place. And if you make the learning rate too low, you can't descend fast enough. You need a lot more epochs to get to the point that you need to, etc. What's up?
So to your example of topology,
Yes.
right? If you were moving in bigger steps, you would jump to the other side of the valley. And then you'd say, oh, downhill is this way. You would jump to the other side of the valley and never get to the bottom. And in the general case, we saw differential equations, right? We differentiated. But remember, the computer's always doing discrete math. So I'm always taking that 0.01. I'm always taking a discrete step. So this problem of jumping too far is always present within a discrete math. You can always find oscillations, so you never actually tend towards a solution whenever you try and do differential equations in discrete math. So,
But can you detect an oscillation and lower?
We'll talk about that.
Okay.
Yep.
Nice segue.
One forward for me.
But you can tune like your learning rate so that at the beginning the learning rate is higher and then
That's what we're going to talk about. Yeah. So before we talk about the slide, I am going to touch on that tuning. Before we touch on this slide, does everyone feel comfortable with either the Carbonara idea or the more technical way of implementing deep learning? Just want to make sure we all understand both. One or the other, not both. We feel pretty good? Okay.
Did we just cover back propagation?
We just covered back propagation. Before that was the forward pass. So we covered forward pass and back propagation.
So the back propagation is when the chef told us the bacon was overcooked,
Mm-hmm.
to update things.
Yes.
Okay.
Yeah. What's up?
So, like, if I were to describe this in less technical language, I have a means to make a prediction. I can say, oh, I have all these things that impact my decision. I have a means to measure how wrong my decision was, and then I have a means to update my method such that next time I'll a little more right.
Correct.
Yeah, one of the keys to this was when you did that -1, that 1 represented saying that photo that was being identified was actually a cat.
Yes.
Right? It should be 100% cat. Definitely was cat. Right? So the key to this is you have to know with your data with your inputs that you're putting in what the expected output is.
Yeah.
So that you can give that to the system so that it back propagates the right way. So, oh, that was supposed to be cat. Okay, let me go adjust something to look for more cat.
Getting warmer, getting colder.
Yeah.
When you need the chef that knows what the ideal bacon is.
Yeah.
Well, hence your training data.
That's your training data. The chef is the true label of your training data. So I think you're very specifically alluding to supervised learning, where your data set, you're going to have 11 rows, and your 11th row is your ground truth label. And so that way the model, when it makes a prediction, it can compare it to the ground truth label and says, oh, I was wrong. So now I need to update it in this way. And then it can say, oh, I was correct, but man, I was 5% away from choosing dog when it was cat. Let's make that better. Is that where you're headed? Oh, okay, cool. Yeah. And there's other ways of there's other things. There's unsupervised learning. There's like partial supervised learning. There's a lot of others, but specifically we're going to focus on supervised learning. It's a lot easier than the others.
Just real quick.
Yeah.
We're probably like halfway on time already.
And we're about halfway through.
Okay.
Yeah. Thank you, though. Okay, so I'm just going to touch on this. I don't want to get any more into the technical nitty-gritty. There's a lot of things that we're going to kind of jump over. One of those is optimization. And so stochastic gradient descent is an optimizer. We've come up with much better optimizers like Adam, which does this decrease or change in the learning rate the further you get into the process. So generally the thought process is we start with a higher learning rate and we decay it as we go so it gets smaller and smaller, so we're taking smaller jumps through that valley. There's also regularization, so models tend to overfit. We want, it gets so accustomed to the training data that it's not as good when you put it on real world data that it hasn't seen. So you apply regularization techniques. And then there's tons of different architectures. You have convolutional neural networks, which are really good at image recognition. You have recurrent neural networks, or long-term, short-term memory networks, which are good for language prediction. You have transformer models, which turns out are pretty good at a lot of things. And then you have diffusion models, which are kind of the premier image generation models. But what I really want you to take away from all of this is that some simple form, they are all doing a forward pass and a backward pass. Convolutional neural networks just don't use y equals mx plus b. They have a much more complicated forward pass. They're still doing a forward pass, and they're still doing a backward pass. Backpropagation was the discovery of the 90s that made machine learning and deep learning possible.
For those of us who are really old, I remember hearing in the late 90s and early 2000s that what was supposed to overtake anything statistical very shortly was genetic algorithms, or in some way that there would be some sort of a random forced evolution.
We're going to talk about that.
So that is coming. Okay. I thought that was entirely cut off. Thank you.
I think it should be coming. I'll elaborate. I think we went to sleep. Thank you, sir. All right, next forward. All right, so we're going to start bridging into humans. So it turns out humans, as a civilization, are really good at updating the function G. Broadly, we got to where we are today, like getting to the moon, curing specific human diseases or identifying human disease, building a car, what have you, because we are really good at cumulatively updating the function. Now I want to propose to the crowd, what about deep learning models? We've made no claims about how they update their G function, if it's good or not. And in what sense is it good?
The sense of matching training data.
Is this an open question?
It is an open question.
Okay.
I would like to hear.
My understanding is most of the stuff is not, most genetic stuff is not doing this. They're using pre-training, and then it's kind of baked in. Whereas other people are trying to do more recurrent learning, maybe, I don't know, reinforcement learning.
Yeah.
Maybe the reinforcement learning, they are trying to make it update, but that's different than most of this genetic pre-training stuff.
So I think inherent in what you just said, I think, is that deep learning models do not continuously update their weights once they are done training. And I'll give it back to...
Unless you consider reinforcement learning deep learning, or is that something else?
It's a different, it's a different field of machine learning and AI. The premier models today, like ChatGPT, use a combination of deep learning and reinforcement learning. Regardless, once we get access to ChatGPT, its weights are frozen. So it can't learn anymore.
As the civilization thinking, each person has a weird mix of a mesh of different pattern recognitions across our lives.
Mm-hmm.
And so we get this like a meta layer of pattern recognizing pattern recognition
Yes.
going. That models themselves aren't expanded enough to start to get into thought experiments
Yes.
of different patterns that they're not really trained for.
Yeah, we're gonna hold on to that. We're gonna hold on to that. No, you did a great job answering it, but I wanna hold on to that. Kevin.
When you think about like none of the models that we use actually change the network topology, right? All of the size of your matrices are fixed.
Yes.
Your softmax function is also going to be fixed.
Mm-hmm.
And you never see major advances in the field unless someone comes up with a brand new model architecture.
Yeah.
It's never from the fact that like my resident model got a little bit better at like detecting or segmenting something. It's like, oh, we came up with a transformer architecture. Like that was the main thing. So right now we just don't. My answer to this is no, because we don't have a deep learning models that creates deep learning models.
Let's hold on to that. So you guys touched on two really big points. Anyone else? No? Okay. Forward, please. All right, the bitter lesson, Richard Sutton, who is widely considered the godfather of reinforcement learning. I know this is a deep learning talk, but he's really cool. I'm going to read it verbatim just so you guys, I don't mess it up. So the actual contents of minds are tremendously, irredeemably complex. We should stop trying to find simple ways to think about them. Instead, we should build in only the meta methods, he's talking to somebody, only the meta methods that can find and capture this arbitrary complexity. We want AI agents that can discover like we can, not which contain what we have discovered. Okay? Part of what stemmed this is all early artificial intelligence was a mix of us putting rules and heuristics. It mentioned meta methods. I don't know if you heard me. I just really wanted you to know that your thing was in there. We were doing a mix of heuristics and trying to build artificial intelligence that way. That was how our premier image recognition models were working up till about 2012. And then we came along with the convolutional neural network, which just uses data to figure out how to classify an image, and it blew every other approach out of the park. And so this is a really good example of we can't bake human knowledge into the model. We have to let the model figure it out itself. Deep learning was one of the first steps of that, but I think we're all on the same page that we're not quite there. It needs more. Next slide. All right, the meta methods. The nematode. I don't know how many of you are familiar with the nematode. It's one of our greatest ancestors. All it knew how to do was move forward and move backwards. It sensed food and it sensed pain. That was all it knew how to do. How did we get from a nematode to the brilliant person that Kevin is? You know the answer.
Genetic algorithms?
Yeah.
Yep.
It's one extra neuron if it's Kevin. Sorry, man.
He's mastered side-to-side motion.
So it turns out humans have a built-in way of changing our architecture, and that is through gene mutation. And so over millions of years, the nematode DNA was mutating such that it was becoming a different organism that was better for its environment, which led it to survive for longer and experience more mutations until after billions of years we ended up where we are today. So I think this is what you were alluding to. The deep learning model architecture is fixed, and it will not change until a researcher comes up with a better idea. i.e. in 2019, Google released the Transformer paper, which led to the blowing up of the LLMs that we see today. Go back, please. All right, sensory intake. We as humans, all the time, are taking in data from our eyes, ears, mouth, I'm missing some, smell, and touch. And that is allowing us to get a continuous update about what is happening in our world. And then we're able to take that information, do something with it, solve a problem, or interact with the world, etc. We know that models can take in data. I can give ChatGPT a new context, right? But it's not continuously getting that sensory input on its own. It's being supplied at very specific intervals, i.e. a human uses it. So that's one of the things that we have as well, right? And then we have this continual learning and dynamicity. As we are talking, blue shirt friend, what's your name?
Ken.
Ken?
Yes.
As we are talking, I'm really hopeful that Ken is learning something right now. That means that his neurons, as we are talking, are transforming themselves. They have plasticity. They are continuously changing as I speak to him, as he looks outside, as he reads a book. He is growing new connections, reinforcing things, and then he can also be in this internal thought loop that allows him to solve problems with that new information that he's getting. And so to me, these are 3 meta methods that are important but are missing, and all of our current, not all of our current AI methods, but as far as I'm aware, not all of our AI methods have all 3. So I'll pause for a moment if you guys have questions. No? All right. Suppose that means I'm doing a good job. Forward, please. All right, what does DL need? The ability to update its architecture. How can we expect a model to get that continuously updating G function if the architecture we gave it at first wasn't good enough to begin with? Do we need a way, are we far enough along that we've figured out the right architecture such that that we can use other methods to update that G function without human input? Or does it need some kind of random way to change its architecture until it finds the correct architecture that will allow it to update its G function? I am proposing that we probably still need this. But I'm open to being disagreed with.
A lot of people proclaim that with a cheap version of it, shall we say, where they're just taking certain layers and they're making them a little bit more dynamic. And it's kind of like a variable placeholder.
So
it's not the fundamental architecture changing. They're just giving the architecture that's there a little bit of flexibility.
Yeah.
And that's you'll hear about a cheap, where they're like, it updates itself, it updates its own architecture. And it's like, yes, in a cheap, low cost way.
Yeah. Something that I think about, and this is completely hypothetical, I don't know if this is possible at all. LLMs are really good at writing code. They can more or less write a deep learning model. Is there a world where you just somehow get a large language model stuck in an infinite loop where it's just pumping out a deep learning model? That deep learning model doesn't turn on, it just died by natural selection. Then it pumps out it just keeps pumping out these different deep learning models until one can actually turn on and train. And then one can turn on and train better than the other. And then one can turn on and train and say, oh, this could be better, I update my own architecture. I don't know if that's possible, but it's just an idea of like, where are we at today? What's up?
So there's 2 ideas here.
Sure.
Andre Karpathy, if any of you are familiar with him, one of the OG OpenAI guys, and he did this with GPT-2 and modern frontier models. So the original architecture of GPT-2 is like kind of inefficient compared to modern methods, and he created these like little explainer notebooks to train GPT-2. He sent like GPT-5 or Opus at them and had them iteratively update the means by which we train GPT-2, and did observe that you can improve training efficiency, improve loss function over time. So like there are explorations currently into using LLMs to optimize LLMs.
Yeah, but have they optimized themselves into a better version? So I don't particularly, I understand the path, right? But if GPT-5 makes GPT-2 into 3, it's not really, a lot of that information's now on the internet and it's been trained on it, right? It's just repeating a process. Not that, but I understand what you're saying.
Yes.
Yeah.
You also have like people from Anthropic, like Boris Kearney, saying we don't write code anymore. Like no one writes code in Anthropic anymore.
Yeah.
Claude is writing our code.
They also accidentally released their Claude code harness. So.
But Claude does get that,
Yeah.
Opus 4.7 is better than 4.6, and if they're not writing the code, obviously there's human input there. It's not fully automated. But
yeah.
there is some training loop wherein Claude is heavily contributing to Claude's own.
Claude is I'm going to push back just a little bit. Claude is heavily responsible for updating the next version of Claude with significant prompting from a human that fundamentally breaks down the argument of what we believe intelligence could be.
And I think I agree. I think the second idea was model collapse, like the idea of training a model on its own outputs.
100%.
And you just get slop, inputting slop.
And we see there was a research article that Saul sent me recently that explored that exact same topic. Like in their minds, they proved that the path we're taking will lead to model collapse, not this G+1 idea.
Sure.
Yeah.
And then the key is it's about evolving the architecture. You can evolve a model within an architecture kind of problem that can do that already.
I ignore you.
So it's that what is an innovative way of creating an architecture about a model that they might not be able to quite do. Or an efficient way might be human beings. It might just be efficient that a world of human beings can do better than a whole bunch of electricity.
Yeah. And not to discount what you're saying, like I think Demis Hassabis, the CEO of DeepMind, is exploring ideas like that, and obviously so are Anthropic and Sam Altman. I personally am always skeptical of the person trying to sell me something that their way is the way that's going to get us there. All right, I'm running out of time, so I'm going to start kind of going through this a little bit more. All right, the ability to continuously take in data from its environment. We need all kinds of sensors on these things. They need to be able to hear, they need to be able to see, they need to, assuming that the humans are the correct approach, they need all of this data to be continuously coming in. Otherwise, they're just going to get frozen at time. Do you guys remember when 2023 GPT couldn't answer 2022 questions? Or it was 2023 and GPT couldn't answer questions about 2023 because it wasn't getting a continuous input of data. You got something, Saul?
When we talk about different forms of data input as well.
100%.
So you point out the cross-entropy function for different labels, but it could also be, in intensity.
Yeah.
So on a continuous.
So something the brain does that our current models can't do, and I think you pointed this out, the brain is converting all of these different signals into one data format, and then it does what it needs to do with it. And so the question is does a deep learning model need to take in and handle many different formats, or does it need a way to take in many different formats but normalize it to one type so that it can do something with it? What's up?
Isn't this sort of what modern LLMs do? Like you can map an audio file, a text file, an image, a video to the same latent space and just predict off of that same latent space. Like I can give ChatGPT an image and it understands that image as if it would understand text.
I think I agree with you. The only rebuttal I would have is it's not continuous. It requires us to keep having to prompt it, right? And then it doesn't do anything with it subsequent to the prompt. But it has the capability of interpreting it into a format that it can understand.
Well, we are mapping things into the same latent space. Like there is like an abstract kind of, I can represent image and text in the same mathematical space. These models do this in some sense. Like
yeah.
Not continuously, but.
Yeah. I'm wondering, I'm stuck on, are these companies just really good at blurring the lines of transformer models and diffusion models? And I don't know the answer to that question. Because if it's true, then that would suggest they're using kind of, two different data formats, not necessarily normalizing it to one. I'm not sure.
So, there are embeddings models that I can give text and image to, and they will produce embeddings in the same latent space that I can query image and text in a kind of unified mathematical space.
Gotcha.
Yeah.
Go ahead, Saul.
You've also got to consider that somebody made a decision as to how to make that transformation between those two data types. Was it an RGB channel for each of the pixels? Somebody made a decision. Whereas in the body, yes, it's transforming it into something your brain understands, but even the mechanism by which that happens had plasticity, so it can change. Yeah.
Yeah, I'm hopeful I'm not coming off as contradictory. I'm more so just trying to say I understand what you're saying. Of my current knowledge, these are the things that make me not so sure, if that's fair.
Yeah, I'm open to disagreement.
Same. Ross is not open to, I'm just the ability to continuously update its G function based on that data. I feel like this one was obvious that it was coming, right? We got to be able to continually learn. If I train a deep learning model today to play chess, and then I try and fine tune it to play, did I say chess? Checkers. It's more likely that it's going to forget how to play chess than it is to learn how to play chess and checkers. And that is why we freeze weights when we release them, because there's this issue of catastrophic forgetting. And so when you look at something like ChatGPT or Gemini, they have to like big bang train it. They train it on everything at once, and then they give it to us. Then Gemini 3.3, or I don't know if they do a little bit of fine tuning in there, but let's say it's a big jump. They go from Gemini 3 to Gemini 4, same process. Big bang train it, freeze the weights, hand it to us. That is fundamentally contradictory to what I believe is needed to hit artificial general intelligence. Next slide. All right, closing remarks. Ultimately, humans are a mystery. Like, we don't actually understand how the brain does most of what it does. We don't really understand consciousness. We're not sure how neurons achieve the things they do enough to be able to recreate it. And so I want to put that out there as, I don't know if humans are the solution to AGI. It may be a completely different approach, but we also don't understand humans well enough to even use the approach properly, which is why you have some premier labs who are just, if they believe that if they could just recreate a squirrel brain from scratch, they would have 80% of what they need to start heading towards this AGI idea. DL is awesome. I just gave a whole presentation about the limitations of DL, potentially, but deep learning got us Claude and Gemini and ChatGPT. Deep learning has the ability to detect cancer just as well as a radiologist can, right? Like, deep learning might be, I don't know, someone correct me, deep learning is most likely involved in how Tesla is building self-driving cars. Like, deep learning is phenomenal at doing very specific things very well. And in LLM's case, it's language broadly. And it turns out you can do a lot with just language. The future is exciting. Deep learning only really became popular in 2015 when AlphaGo beat the world's best Go player. We're 11 years into this process. That's it. And people are already saying, we figured it out, go quit your jobs, it'll be here soon, right? But we still have three fundamental, in my opinion, we still have at least three fundamental problems to solve. And so to me now is like, it's never been more exciting to be in the career field that we're in, because we can contribute to these kinds of things. And that's all I got. So, what's up?
Well, shoot on that. In terms of memory, we have a model that shows some form of memory. I've heard it referred to as a really good form of compression, simply by turning things into, as you say, a function and guessing the next output based on what was presented. And when you inspect that output, you can see that it seems to have encoded things inside of it. Does anyone have any idea if that is now roughly, like, maybe this is how human brains work? Previously, there had always been analogies of encyclopedias or things that were very, huge storehouses of memory that simply sat idle, but actually had the bits and pieces in it, as opposed to something mathematically compressed that was simply too complex until you send the right signal through it. Is that, I don't know if the question makes sense.
Yeah, I think the only way I know how to answer your question, and it might not be good enough, is that I think it's the general consensus is that the brain isn't doing a forward pass back propagation methodology. And that's what all of our deep learning kind of models are based off of. And so I know that's probably a really non-answer because I'm not sure I quite understood your question, but I think it's really like we're still not even sure what that mechanism is in the brain that's like doing the things that we want something to do better than us.
And the main thrust of my question would then be, has the fact that we have clear working experiments, as you, on point number 2, Deal was awesome, that has made anyone rethink their own models that they were trying to test of exactly how the human brain works? We have something else that works. Is there a match?
Yeah.
Is there?
I'm not sure, but you just reminded me of something that I wanted to tell you guys about. There's kind of three big things happening in the field right now. Ilya Sutskever left OpenAI and started his own business. He is looking for completely different algorithms to head towards AGI. I think he's kind of moved away from LLMs as being the answer. Demis Hassabis, I'm sorry if I'm butchering his last name, I think he believes that LLMs play some sort of role in that, but he's also at the moment building world models as a place that actual like agentic models can interact in and try and learn in. And I don't know what Jan LeCun's doing, but he left Facebook because he didn't agree with their approach on AI, but I don't know if any of you guys can have insight into Jan LeCun. And so we do have this like branching off of very brilliant people exploring other approaches to see how they can get us to this idea. Richard Sutton, the guy whose quote I used, is trying to build an Alberta model, which is based on reinforcement learning. And I think 2 of his principles are it's going to have continuous data input, and it can only learn on active compute, if that makes sense. There is no pre-training than this. It is real-time compute that it is learning on. What's up? You had your hand for a while.
More questions, maybe we can give Mike a round of applause. Just in case anyone has to duck out early. Guys, we're getting close to 3, but we can do more questions if you can stick around.
I'll stick around. I appreciate you.
Yeah, you as well.
Yeah. What's up, Kevin?
So, like, regarding the thing with, like, updating its architecture, this is relatively well studied within the field of genetic programming and genetic algorithms. The problem is the fact that, you know, in genetic programming, you have something called a fitness function, which is analogous to something like a loss function. The problem is the fitness function is the most expensive part in genetic programming.
You said it is?
It is the most expensive part of genetic
Such that it's prohibitive?
It is prohibitive. The ability to update its architecture and create a better architecture is not a technical problem, it is a scale problem.
It's a computation problem.
Right, so if you think about it, if you're trying to create a better version of, say, GPT, right, of the transformer model, in order to, quote unquote, evolve a better version, right, you have to train every single subsequent, you know, mutant or individual on the entire corpus of one of the original GPT. That is the only way you're going to be able to evaluate whether or not that model is good. So yes, you can update the architecture. The question is, do you have enough money and do you have enough time to do it? Because what you're actually trying to do is to create offsprings with different mutations, and in this case, different mutations will be different model architectures. The only way to evaluate whether or not that model architecture is good is to now train that one individual on the entirety of the text that humans have produced.
Yeah.
Again, my point is being number 1 is that it is purely a problem of scale, money, and time.
Yeah, so that might be one of those things. We knew about convolutional neural networks way back in like the 80s and 90s, but the compute just wasn't there to make those things work the way people wanted them to. And the same thing with diffusion models. Diffusion models were coming around in the early 2000s, and they just weren't performing. But as GPUs started getting better and we started getting better access to better compute, all of a sudden these historic methods just came out of nowhere and blew away the present state. And so it might be one of those cases where there's some innovation that'll occur, and then this will just pop out of nowhere and completely change the way we think about how we build models.
One can hope, right? I mean,
and that's why my point earlier was that human beings might still be the most efficient way to get better iteration on models for now.
For now.
Electricity. It's like,
yeah.
Just grow it humans, let them learn, and let them come up with ideas.
Yeah.
How many calories does it take to get 0 years old to like, 30, 40.
Well, but they're also living a life. So if you get more geniuses, you kind of get them for free.
Yeah, I think the computation and energy thing is maybe like a meta problem that deep learning needs, the more computationally efficient models and also the economic stuff like the energy.
But also data efficiency, right? Like,
Yeah. Well,
humans can few shot a problem. There are some models that can few shot a problem, but nowhere near how a human can.
But if you can only few shot a thing that is remote trained in. So it's not really saying, few shot it. No, like I can't one shot open heart surgery.
I can see a zebra once and know what a zebra is. I don't need to see 10,000 images of a zebra to get an 80% probability that it's a zebra.
Also, you might mess up on a referee.
Yeah, you're okay.
Somebody